So welcome everyone. Welcome to the pre-seminar. Today we're happy to have Yibo Gao from MIT, and he's going to talk about, it's a different title, root system and, is that the, wait,
No,
is this the right slides?
That is only the pre-seminar.
Okay. Okay, so he's going to talk about root system and Billy Postnikov patterns in combinatorics.
Yeah, thank you very much
feel free to ask any question.
Yeah. Thank you very much for the introduction. So I have separate slides here, and also it doesn't seem like it's working because it's not flipping. All right, so I need to retry this. Share again. Oh, okay, so now it's working. Nice, all right. So the goal of this pre-seminar is to advertise the philosophy of generalizing stuff from type A or the symmetric group to other types. Sometimes, of course, it cannot be generalized, but sometimes it gives you even better things. I think it's a little bit related to the background of my talk, but it's really the same philosophy. So I will talk about root system and Weyl groups, and then Billy Postnikov patterns, and some examples. Feel free to ask any questions. Can you hear me well?
Yeah.
Okay, cool. All right, so this is the axiomatic definition of a root system. Basically, I have a ambient vector space E, and a root system is a finite set of vectors. Right. Okay, so let's actually go through these axioms. So first, it spans E. Well, if it doesn't span, you just take E to be the space that they span. And right, so the only collinear vectors in this root system are alpha and negative alpha. The third condition is some integrality condition called crystallographic, which is not so important, I guess, for this purpose. And finally, we have, so this sigma alpha. So alpha is some vector, and there's a hyperplane perpendicular to alpha. So this sigma alpha is the reflection across this hyperplane. So the last condition just says that, I mean, if I reflect any roots across some other roots, then I still get the roots. So it lies in phi. Right, so basically, there are just a bunch of vectors that are really symmetric. So once I have a root system, I can pick a generic hyperplane that will partition this root system phi into positive parts called phi plus and negative parts called phi minus. And correspondingly, we are going to have a unique set delta of simple roots such that first, they are a basis of my ambient vector space. And also, the second condition is pretty interesting. It says that every positive root can be written well, first, because delta is a basis, so it can be written as a unique linear combination of the simple roots. But once you do that, then all the coefficients are going to be non-negative integers, in fact. So for example, here, this part is the positive part, and I choose alpha 1, alpha 2 to be my simple roots. And each vector, so for example, this guy can be written as 2 alpha 1 plus 3 alpha 2, and all the coefficients are non-negative integers. So phi is irreducible if it cannot be partitioned into two parts that are orthogonal to each other. Irreducible ones can be classified by thinking diagrams. It's a picture from Wikipedia. We have 4 classical families and some exceptional types. The Weyl group is a finite subgroup of GLE generated by all the reflections across the root. So those sigma alphas that's defined earlier. Or equivalently, it's generated by the reflection across the simple roots. Let's L of W denote the standard Coxeter length. And for a Weyl group element W, the inversion set is the set of positive roots that get sent to negative roots. Yeah, it's standard fact that the length of W equals the size of the inversion set. All right, so here's an example of type A sub n minus 1. So my root systems is given by all the EI minus EJs, where EI is the standard coordinate vector. And I can choose a generic hyperplane, well, a hyperplane, and that will give me a posit roots with EI minus EJs, where I is less than J, and correspondingly, I'll have a set of simple roots consisting of all the EI minus E sub I plus 1. So for example, you can see that EI minus EJ can be written as EI minus E sub I plus 1 plus E sub I plus 1 minus E sub I plus 2 and so on. So each EI minus EJ is a non-negative integer linear combination of the simple roots. Right, and I have these reflections, and you can easily see that it just switches the values accordingly, I and J. And because of this, the Weyl group is isomorphic to the symmetric group on n elements. And also for a permutation, we can see that because W sends EI minus EJ to E sub WI minus E sub WJ, then EI minus EJ is in the inversion set of W if and only if WI is greater than WJ. So any questions?
Sorry, I missed the first few minutes, but how do we know that these reflections are going to leave the other coordinates fixed, I guess?
This you can write down basically explicitly how this works on
I mean like in general, I guess. Do we know that? So the reflection is like we send the element in question to its negative and fix its opposing hyperplane, right?
So it is so when I have alpha, I have a hyperplane that's perpendicular to alpha.
Oh, I see. Okay.
And what this thing does is it sends beta to the reflection across this hyperplane. So it can be written as beta and add some multiple of alpha.
I see, yeah.
And what it says here is that no matter what this guy is sent to, the difference between these two will be a multiple of EI minus EJ. So all the other coordinates are unchanged.
I guess it's just too late for me. I'm sorry.
Hmm?
No, I'm just I guess I just need to get here on time.
All right, sounds good. Okay, any other questions? Okay, so yeah, so let's talk about Debye-Postnikov patterns. So first, we have this very useful proposition. The inversion set of W, so recall that the inversion set is the set of positive roots that get sent to negative by W. So the inversion set of W uniquely characterizes the Weyl group elements. So in other words, this map I sub phi from the Weyl group to all the subsets of phi plus is an injection. So basically, you can characterize the permutations by its inversion, and that should be obvious. So you might want to ask, like, what is the image of this map? So S, which is a subset of phi plus, is the inversion set of some Weyl group elements if and only if we have this biconvex condition. That says that if I have alpha beta in S, and if their sum is a positive root, well, both are positive, so their sum can only be positive, then their sum is in S. And if none of them is in S, but alpha plus beta is still a positive root, then alpha plus beta cannot be in S. So both S and the complement of S are convex. Right, so in terms of permutations, this says that if Wi is less than Wj and Wj is less than Wk, then I have Wi is less than Wk. And yeah, this is not a typo. This should be in. All right, so if we let E prime be a subspace of E, so E is our ambient vector space that everything lives in, then so now I'm going to restrict a Weyl group element to a subspace. So phi prime. Oh, by the way, this proposition is not that easy, but it can be done. It's pretty classical. So phi prime, let phi prime be the intersection of E prime with my root system phi. So you can check, the axiom is still a root system. And if I intersect with only the positive roots, then I get a set of positive roots. So correspondingly, I will also get a set of simple roots, which is going to not be a subset of the previous, of the larger set of simple roots. But that is fine. So when I have W that lives in the larger Weyl group, I know that its inversion set is biconvex. Okay. And you can check this biconvexity condition that the intersection of my biconvex set with this smaller subspace is also biconvex. Okay. This is not very hard to check. It should be very believable. And then because of this first part of the proposition, because this is biconvex, so there exists a unique W prime living inside the smaller Weyl group, such that its inversion set is this restriction. Okay, so this is how we are going to define restriction map from a larger Weyl group to a subspace. Right, any question? Oh yeah, so let's take a look at an example. Not yet there, but okay. Also, this is just recall last slides. The restriction to phi prime is the unique W prime in the smaller Weyl group such that its inversion set is the restriction of the inversion set. And as you may guess, we'll say that W, which lives in the larger Weyl group, avoids the pattern W prime in the smaller Weyl group if there does not exist a subspace such that your restriction is the pattern. Okay, so here's an example. So let's take W equals this permutation. So this permutation has 7 elements that live inside the Weyl group of A6. So consider E prime to be the span of these two vectors, E2 minus E4 and E4 minus E5. Then this phi prime is of type A2, right, with a set of simple roots, E2 minus E4, E4 minus E5, and the other positive roots is E2 minus E5. And I can identify them as new coordinates. It's E1 prime minus E2 prime and E2 prime minus E3 prime. Right, so now I look at the intersection between the intersection of the inversion sets of W with the subspace E primes. And I want to know whether, for example, whether E2 minus E4 is in my inversion set. So E2 minus E4 is in my inversion set if and only if 3, which is the second element, is greater than 7, which is the fourth index. But 3 is smaller than 7, so E2 minus E4 is not in my inversion set. It's not in this. And then I check whether E4 minus E5 is in the inversion set. And because 7 is greater than 2, so E4 minus E5 is in my inversion set. So I have E4 minus E5. I also have E2 minus E5 because 3 is greater than 2. So with the identification with the E primes, I can write it as E2 prime minus E3 prime and E1 prime minus E3 prime. So this is the inversion set. And I need to translate this back to some permutation on 3 elements, and that is exactly 2, 3, 1. So what you are doing here is you look at indices 2, 4, 5, which is 3, 7, 2, and then you just flatten it and you get 2, 3, 1. And so this is exactly the sort of the pattern containment. All right, so any question? Okay, so the main takeaway is
sorry,
that,
could I ask a quick question?
Yeah, for sure.
So the inversion set, when you do the restriction, should be a subgroup of the Weyl group on the original set as well, right?
It's a subgroup.
Sorry, not the inversion set.
Yeah.
But like when you do the restriction, the Weyl group on the restriction phi prime, that's going to be a subgroup of the original Weyl group.
Yeah.
Okay. Cool. I just wanted to check that.
So the main takeaway, as I said in the beginning, is that whenever a Coxeter theoretic definition is possible for your favorite class of permutations, defined or classified by pattern avoidance, you could ask for a Billy-Postnikov pattern characterization in other types, if you can find one. So for the rest of my talk, I mean, the pre-seminar, I will just list some examples. Oh, by the way, I should mention that this Billy-Postnikov pattern is invented to study smoothness of Schubert varieties, where you characterize the smoothness criterion by pattern avoidance. But since I don't know much about geometry, I will just talk about some combinatorial applications of this pattern. Okay, so for example, a Weyl group element is fully commutative if no reduced, okay, so this should be reduced word, if no reduced word of W admits a break move. And it's not hard to see that a permutation W is fully commutative if and only if it avoids 3 to 1. Okay, so here is example. I think I also have this example in the main talk. So in S4, W being S2, S1, S3, S2 is fully commutative because you cannot have like a S2, S1, S2 or S2, S3, S2. I need like Si, S sub I plus 1, Si, and apply a break move there. So this is fully commutative and it also avoids 3 to 1. But this thing is not fully commutative because you can use a commutation move to switch S1, S3 here. And then you can apply a break move S3. So you have a 3, 2, 3, which you can replace by 2, 3, 2. So this is not fully commutative and it contains 3 to 1 at 4, 3, 2.
So were moves and braid moves defined earlier?
No.
Then what are they?
It's wait, can I try to see? I don't think. Not sure if I can. Yeah, I don't know if I can draw on this, but yeah, a break move is basically, I mean, in type A, it is S2. It will look like Si, S sub I plus 1, Si, and you can change this to S sub I plus 1, Si, S sub I plus 1.
So what's a move in general then?
Oh, it's something that you can do to the reduced word to get another reduced word. So for example, a commutation move. So here I have S2, so 2, 1, 3, 2, and S1 and S3 commute. And you can, so W also equals S2, S3, S1, S2. And you can say that I have applied a commutation move.
I see. And what does it mean for a move to admit a braid move?
Sorry, this should be a reduced word. It's a typo here.
Okay, what does it mean? Oh, so
Yeah, I really wish I can draw something, but I don't know how I annotate on iPad. Well, maybe I should get my slides. Oh.
So fully commutative. So there are only two types of moves: the commutative move and the braid move.
Yeah. Usually you call them like a commutation move and a braid move or a Coxeter move, but the braid move can be different, can have also like different types. So so for example, in type B, they will be a bit different. But either way,
so the braid move on the S3, S2, S1, S3, it's like basically A is S3 and B is S2, S1, and so we replace it with S2, S1, S3, S2, S1. Is that what's going on?
So what you yes. So maybe let me just type something in the chat. Yeah. So you have W equals 3 S3, S2, S1, S3. So you can apply a commutation move to get 3, 2, 3, 1.
Oh, I see. So it's not a compound braid move. It's not. It's not like we're treating the 3 as the outside thing and the 2, 1 as the inside thing. Okay. I see.
And then you can apply a Coxeter move because S3, S2, S3 equals S2, S3, S2. So you have some reduced word of W that emits a Coxeter.
Is it true that all reduced words can be gotten between by these moves?
Yes. Yes.
I see.
Some pretty old theorem by Tis, I think. Tis Lemma. I'm not entirely sure about the names, but yeah, this is true. Okay, all of these are not important because these are just examples of the things that you can do with generalization to other types. So fully commutative elements are just one set of examples. So it's just one example. So what about, so this is in the original paper of Bilya and Postnikov. So an element W is fully commutative. So in an arbitrary Weyl group, if and only if W avoids the longest elements in all irreducible rank 2 root system. So basically, this is something that you can characterize by Bilya-Postnikov patterns. Yeah, so all the root subsystem of type A are also type A. So in terms of symmetric group, it just means that you are avoiding the longest element in type A2, which is the longest permutation of 3 elements, which is 3 to 1. Okay.
Sorry, how do we define the length of an element of a root system?
No, this is.
Did I miss that? I'm sorry.
Did I? Oh, I mean, all irreducible longest elements in in the Weyl group of all irreducible.
Oh, okay, in the Weyl group.
Yeah. You're absolutely correct. Yeah, it should be the Weyl group. Yeah, longest elements of the Weyl group of all irreducible rank 2 systems. Nice. Yeah, I mean, I have like 4 examples left, but we don't have to go through any of them. Let's see. So this one, permutation W, element W is called Boolean if the interval below W in the strong Bruchau order is a Boolean lattice. So permutation is Boolean if and only if it avoids 3 to 1 and 3 4 1 2. So this is S3, the strong Bruchau order of S3, and you can see if I'm the interval below 3 to 1, it will be the whole thing, and this is not a Boolean lattice. But if I'm 2 3 1, then this part is a Boolean lattice. All right, so this is my work with undergrad. we use Billy-Posnikov patterns to characterize the Boolean elements with this list of Billy-Posnikov patterns. So this is not such a long list that you think it is, because previously Tanner showed that the Boolean elements, so being Boolean is equivalent to avoiding 10 patterns in type B and 20 patterns in type D with some other sense of pattern avoidance. But here we only have, well, if you look at type D, so type D has subsystem only of type D and type A. So you only have like 1 pattern in type D and 2 patterns in type A. So it really saves you a lot of efforts using Billy-Posnikov patterns. So, okay, so separable elements. So these are given by talks by Christian in your seminar last semester, I believe. So permutation is separable. It avoids 2413 and 3142. And it has some very nice properties and a very complicated definition in other types and some pattern avoidance. So not so complicated. Oh, and after this point are some open problems. So for example, this thing is, when is the, when should I stop? Is it like 25 minutes or 30 minutes or?
You have about 3 to 4 minutes.
Okay, sounds pretty strict. So an element is chromopragmatic if the number of regions in the immersion arrangement of W, that is some hyperplane arrangement associated to W, if the number of regions is the number of elements below W in the strong Poisson order. Okay, so this theorem says that a permutation W is chromopragmatic if and only if it avoids some permutations. Oh yeah, so this, yeah, all the smooth elements are chromopragmatic. It can be viewed as like a, or either way, yeah, it has some connections with smoothness. So Alexander Wu showed that elements in type Bn is chromopragmatic if and only if it avoids a lot of patterns. So you can also ask this question in general, but you won't expect the answers to be so nice. Oh, let me just stop here. There are some more examples, but thank you for listening. All right, any questions?
Do you have any question?
What is the type of a root system?
Oh. Irreducible root systems can be classified by these types: type A, B, C, D, and some exceptional ones. Here.
I guess I don't really understand what this, how those describe the system, but I think there's some connection to Lie algebras, right? I don't really know what
that's right. Yeah, that's right. So either way, this diagram here means that. So for example, let's take type AN. I will have, so each node here is a SI, is a simple generator, SI. It's a generator of the group. And I'm taking the group generated by those elements.
What group? The Weyl group?
Yeah, the Weyl group.
Okay.
So the Weyl group is generated by each of these SIs, more some relations. And I'll have each SI squared equals 1. So that's a relation. Each SI is going to be an evolution. And also for each edge here, this means that SI, Sj to the third power equals 1. So for a single edge, it's Si, Sj to the third power equals 1. For a double edge, it's Si, Sj to the fourth power equals the identity. Because if Si, Sj squared equals identity, it just means Si and Sj commute. So it's not really
right. So AN means that the Weyl group is the symmetric group.
That's right. Yeah.
I see. And then you've got. Okay, and what about the arrows? Like, what's the difference between Bn and Cn?
So the Weyl group is isomorphic but the roots are not. So the root system are different. You can think about this arrow as this root is longer than this root.
Sure, yeah, I mean, they're vectors
So
after all.
So for example, in type Bn, this guy is something like En minus, so let's say this guy is something like E2 minus E1. And this guy at the end is just E1, which has length 1, but this E2 minus E1 has length square root 2.
I see, okay.
And for type Cn, this guy is going to be also E2 minus E1, which has length square root 2, but this one will be 2 EI, 2 E1, which has length 2. So you point in this direction. I actually, this is not a good explanation, but it's one way to do it.
Any other questions? Okay, well, I saw some of you plotting silently. Let's just unmute ourselves and thank our speaker. Thank you.